Let's try to solve this question here. So through what potential difference must electrons be accelerated? So they're interested with the accelerating voltage, how much should it be? So that they will have the same wavelength as an X-ray of wavelength 0.150 nanometer. Okay, so you want your electron to be having the same wavelength as the X-ray. So in terms of mathematical equations, we can say that the wavelength of electron is the same as the wavelength of X-ray. So let's just call it as X, and we are given with the wavelength, which is 0.150 nanometer. Okay, so now they are interested with the potential difference that the electrons be accelerated. So they are interested with the accelerating voltage. You have to relate it to the wavelength. So there's quite a few steps we need to do. We need to relate it to kinetic energy, then momentum, then wavelength. Okay, so how do we get the equation? First, we start with the relationship between accelerating voltage and kinetic energy, which is K is equal to EV. K of electron is equal to EV. Since it's electron, then this equation is valid because this is elementary charge, no problem. But now we are going to substitute this K over here with P squared over 2m to continue extend it until you reach the wavelength. So K replace it P squared over 2m. So this will be P squared over 2m. This is mass of electron is equals to EV. Okay, then afterward we are going to extend it further by saying that P is equal to H lambda, H over lambda. So H over lambda square over 2 mass of electron will be equals to EV. Okay, so if you want to rearrange it, you can put the accelerating voltage on the left hand side. Then what's left on the right will be H square divided by 2me E K lambda square. Okay, so this is your equation. Then now it's just substitution. So Planck constant 6.63 times 10 to the power of negative 34 square divide by 2, the mass of electron 9.11 times 10 to the power negative 31. The elementary charge is 1.60 times 10 to the power negative 19 coulomb. Then our wavelength here will be 0.150 times 10 to the power of negative 9. And of course, your wavelength has a square, so do remember to square it. So if you calculate it, you get an answer which is 1.00 times 10 to the power of negative 8 volt. So this is the voltage needed in order to obtain this wavelength over here. So it's quite a very low voltage actually. Okay, so you can easily create an electron that has a wavelength of 0.15 nanometer by accelerating it through this small potential difference over here. Okay, so that's question A. Next, for question B, they want the electron to be accelerated so that they have the same energy as the X-ray in part A. So that means for question B, the relation is not saying that the wavelength is equal. Instead, they're saying that energy is equal. So they want the kinetic energy of the electron to be having the same energy as the X-ray in part A. So X-ray is a form of light, right? Okay, X-ray is an electromagnetic wave, so it's inside the electromagnetic wave spectrum. So all of them are electromagnetic wave represented as a photon, gamma. Okay, so K is equals to E of gamma. K is because it's kinetic energy, because we are talking about it moving, so you can talk about it in terms of kinetic energy. But we are talking about light, because light or photon, they are massless, so it's inappropriate to call them kinetic energy, so we just call it as E energy. Okay, so you can know that the energy for light, you refer for light energy, how to relate it with wavelength of 0.15, you relate through this equation, hc over lambda. So K is equal to hc over lambda. Okay, so this is the lambda of the photon. Okay, you can try to calculate it, 6.63 times 10 to the power negative 34. Your C will be equal to 3 times 10 to the power negative 8 power 8, sorry, not negative 8. Then your lambda over here is a lambda given in A, which is 0.150 nanometer times 10 to the power negative 9. Okay, so this is the left hand side. On the right hand side, how do you relate K, the kinetic energy over here, to the potential difference that electron must be accelerated? So you relate kinetic energy to the accelerating voltage over here. So K is equal to EV, so you can replace this K over here with EV. Okay, so now if you continue with the substitution, maybe I should bring the e to the other side already. Okay, so I'm going to bring e to the right hand side, putting it as a denominator. So over here I'm going to remove the e. I'm going to put the e at the denominator straight away. 1.60 times 10 to the power negative 19. Okay, hope you understand. We are shifting the elementary charge to the right hand side denominator, so I add it over here. So if you calculate everything, you get the accelerating voltage to be equals to 8287.5 volt. Okay, so now you can see if you're comparing in terms of wavelength, to have the same wavelength, right, you need a very minimal accelerating voltage for it to occur. But if you want the wavelength of the electron to, if you want the energy of the electron to match the energy of the photon, then you need a much higher accelerating voltage. Okay, but usually when we talk about electron microscope, we usually talk about in terms of wavelength. I think I'm not really familiar with electron microscope. It's not my field of study. But here you can see that if you want to match the energy of a usual photon, it requires a greater amount of accelerating voltage. But if you're just trying to match the wavelength of it, the voltage needed for it to happen is actually quite small. So this is the kind of observation that I can see from this question over here. Okay, so that's it for this question. Just need to be careful what is equals to what, then you'll be able to solve this question using this little mind map over here. So that's it for this question. Thank you very much.